Welcome. In this session, we'll learn the concept of discharging of a capacitor. Let's start. So to learn this concept, what we are going to do, we're going to have the example of a RC circuit. And suppose this RC circuit is connected to a source V of S through a switch. Right, and so we say the switch is in position 1, and what we assume that the capacitor is initially charged to some voltage V0. Let's assume this capacitor is charged to this voltage V0. In other words, we say Vc of t is equal to V0 at t equal to 0. Let's suppose it. What we do at t equal to 0, we are going to connect this switch to the position 2. That's what we are going to do, right? And see the behavior of this capacitor voltage after we connected this switch to the position 2. Now, how do we draw the equivalent circuit for t greater or equal to 0? This is the circuit that's valid for t less than 0. So for t less than 0, this is the circuit. Well, for t greater than 0, what's the circuit? What does this circuit look like? So if the switching action takes place at t equal to 0, and we are assuming the capacitor is charged to some voltage V0 at t equal to 0, and we are changing this position of the switch from 1 to. All right. Now the equivalent circuit of this you can draw from this. The circuit looks like this. So this is the RC circuit, and now it's connected to the position 2. The switch is connected to the position 2. As you can see, we don't need to draw this part of the circuit. Why? Because this is not connected to this RC circuit. So we don't need to draw this here. We can simply write it Vc of t, and this is the capacitor. And we want to study the behavior of this capacitor voltage for t greater or equal to 0. All right. So again, to do the analysis, let's apply KCL here. Let's apply KCL here, and let's assume the current that leaves in this branch is I1, and the current that leaves here is I2. So by KCL says I1 plus I2 must be equal to 0. Now what's I1 here equal to? I1 is the current that flows through this resistor. Now what's the voltage across this resistor? The voltage here is Vc. So what's the voltage here? It is 0 because it is connected to this node. So it is 0. So the voltage across the resistor is Vc. So the current that flows here will be Vc divided by R is the current that flows through this resistor. Now what is I2? I2 is the current that flows through this capacitor C. So we know the capacitor current is given by this expression dc dv by dt, and this is equal to 0. All right. Now again, we are going to use the concept of linear differential equation. How we solve the linear differential equation, we are going to use that in this. So let's bring it in the linear differential equation form. So the equation looks like this: dcv by dt plus 1 by rc. What we have done, we have divided both sides by this c, and this is equal to 0. Now this is in the linear differential equation form. What's the general form of a linear differential equation? The general form looks like this, where y is a function of time. So this is y, py is equal to q. Here q is equal to 0 and p is equal to 1 by r. So you can compare the two. If y is equal to vc of t, then p is equal to 1 by rc, q is equal to 0. So what we do, we multiply both sides by, how do we solve a linear differential equation? We solve it by using the concept of integrating factor. So what's the integrating factor for this difference? It is simply e to the power of pt, p dt. How much is p here? P is 1 by rc. So it will be simply e to the power of 1 by rc dt. And this is simply as t by rc. So the integrating factor for this linear differential equation is e to the power of t by rc. Multiplying both sides by this integrating factor to this linear differential equation, what we'll get? We'll get e to the power of t by rc dvc by dt plus e to the power of t by rc divided by rc vc of t is equal to 0, because when you multiply e to the power t by rc with 0, that will be equal to 0. All right. So we can write this left hand side, we can write as d by dt of e to the power of t by rc vc of t is equal to 0. How? Because we can use the product rule of differentiation and we'll get these terms back. If you check it, you can verify the same. All right. So integrating both sides. So now integrating this, what we'll get t by rc vc of t, integrating both sides dt. This will be integration of 0 plus some constant of integration. Integration of 0 is 0, so it will be simply constant of integration. Now this dt and dt cancels. This d cancels with this integration. We'll have e to the power of t by rc vc of t is equal to some constant of integration. All right. So what's vc equal to? Because our goal is to obtain what's the capacitor voltage, what's the behavior of this capacitor voltage. It will be simply k times e to the power of minus t by rc. If you divide both sides by e to the power of t by rc, this will be the capacitor. Now let's eliminate this constant of integration. For this, what we'll do, put t equal to 0. We'll say vc of 0 is equal to k. Now what's the value of the capacitor voltage at t equal to 0? That we have assumed that the capacitor is initially charged to some voltage. Let's suppose it is charged to V0. Right? And V0 can be anything. It can be equal to Vs, it can be anything. Okay, let's suppose that's equal to V0 for general. Okay, that's the capacitor voltage. Vc of t will be equal to V0 e to the power of minus t by rc. All right. So this is the behavior of the capacitor voltage for t less than or equal to, for t greater or equal to 0. So this is the voltage across the capacitor for t greater or equal to 0. So the capacitor voltage is equal to V0 for t less or equal to 0, and this is equal to V0 e to the power of minus t by rc for t greater or equal to 0. All right. So this is the capacitor voltage. This is the behavior of the capacitor voltage. All right. For this RC circuit. All right. RC circuit, which is initially charged. Now, how do we use it in this concept? We assumed that it was initially connected to some battery. Okay, that's when this switch was connected to at position 1, and it charged the capacitor charged to some voltage V0. Now V0 can be equal to Vs itself. Okay, depends upon how long you have connected this capacitor to this source voltage, means Vs. All right, that will govern the value of this V0. Now, what was the aim? Aim was to check how will the capacitor voltage behave after we remove this switch from position 1 and connect it at position 2. Right? This gives us the discharging behavior of this capacitor. So at any instant of time t, the capacitor voltage is now V e to the power of t minus RC. And if you plot this, if we plot this signal or function here that we obtain for this capacitor voltage, if we say this is the time axis and this is the amplitude axis, and we are saying this is the capacitor voltage, and we assume that the capacitor is charged to V0 at t equal to 0. That's what we assume. And what's the behavior of this expression for t greater or equal to 0? The expression looks like this, that it is going down. As t increases, you will see if you plot this equation, if you use the value of r and c, some value, for example, r is 1, c is 1, you'll see the behavior looks like this, means the capacitor voltage decreases as t increases. And at t equal to infinity, the capacitor voltage will be equal to 0, means it will be fully discharged. All right. So this is how a capacitor discharges. All right. Now, in the previous session, we will learn how a capacitor charges, and in this session, we will learn how a capacitor discharges. Now, in the next session, we are going to learn the same thing about the inductor, how in the inductor current changes, varies as we connect a source to this inductor. All right. Let me end this session here.